Welcome back to Old School Coding, where I'm creating a old school simulation of some old school microcomputer products in old school C. So just to review, that's using C99, which encompassed a lot of the standard practices of the time. And I'm trying to use the development processes that I used back in that time period. And what we're simulating are microcomputer components that would have not been out of place in that time period. So far I've done some support code, and I've been pecking around at the modules that are simpler. I'm delaying doing the actual processor until I've got enough of the rest of the system built up so that we don't have to stop and write huge swaths of boilerplate to wait for this address and return this value and so on. So we have our clock generator, we have our system controller, which drives the control bus. We have our decoder, which is going to give us the ability to say, notify me when there's an access, read or a write from memory in this range. So the next step is we're going to start building a RAM chip. Well, RAM board, actually. Surprisingly, RAM chips of the day were not large. Who would have guessed? And the workhorse chip that I am going to be building my simulation around, let me bring up the thing here. I will turn on the PDF viewer if this is, yeah, there we go. That's the wrong one. I am going to be building a memory board, a simulation of a memory board, which uses these 8107B-4 chips, which is the 4 kilobit dynamic memory. And the idea is that you put 8 of these side by side, drive bytes, and they have a suggested layout for a board here, which I've made the thumbnail, where you put 4 sets of those together to make a 16 kilobyte memory board, and that actually fits neatly on a S100 PC board, which was the standard of the day. I think the memory card I had in my old Sol was pretty much this design. The difference would be, of course, that if you are working on a Sol or an MSI or an Altair or whatever, you are plugging in a card about yay big into a S100 bus, which is 100 pins of goodness. And we're not actually simulating an S100 here. What I've got instead is I have a model of what is on the address bus and a model of what's on the data bus and the control signals. And then I have this decoder that gives me the ability to say, hook me up to this page of memory or this I/O port. So some of this board is going to get replaced by the logic from our simulation. So our board isn't going to be exactly the same as their typical system. What we have instead is we will create one edge that's going to drive all these guys to read, and one edge that's going to drive all these guys to write. And ditto there, and ditto there, and ditto there. But we're not actually going to do that. I am going to not simulate the chips on this board. I'm going to simulate the behavior of the board as a whole, okay? Using the fact that I've got the address bus, the data bus, and the ability that I can ask for read and write to be notified of reads and writes within a given range. I anticipate that the RAM module is going to be fairly compact. So again, it's going to be mostly that testing boilerplate that I've been turning out. This won't be as simple as some things. I bet it's going to be simpler than the 8224 and the 8228 though, because this is going to be not a whole lot of stuff here. So let's move the PDF out of the way and let's get to writing some code. So this is called RAM 8107 X8X4. I'm going to give it a nice long name to describe what it is. It's 8107 chips, and there's going to be by 8 wide by 4 tall .h. There we go. Okay. So that compiles, but of course, it's an empty translation unit. So now let's bring in our boilerplate. I'm going to read decode, decoder.h, 8107x8. The reason why I want to be so specific on the name is it is possible in the future that we'll have other kinds of RAM. We may even have different organizations of the 8107. So be that as it may, I could have just called this RAM 16KB. 16 KIB of memory for 8080-like microcomputer system. This module expects to connect to the address and data bus and provide and attach memr. I should say bar RD and bar WR to the decoder to provide 16 KIB of memory to the simulated system. It is notionally modeled after a memory for making use of 8107B-4 memory dynamic memory chips wide by 4 rows for a total of 16 KIB of memory. Chop those off. Address buses and data bus. This is a memory card. It's going to jam in the system. It doesn't care who owns this stuff. It just needs access to them. We're going to get a read signal and a write signal. They're going to go low at the beginning of the period and go high at the end. We are going to provide the actual results immediately. So at the beginning of the read, we will be presenting the results. And at the beginning of the write, we will be capturing the data. So don't strobe these until you're ready. We will not be doing anything when those signals go back high again. And for state, what I'm going to need is byte storage. Actually, I'll call this data. No, I won't call it data. How about RAM? And we are storing 6384 bytes of memory. So how about we do one left shifted? Well, let's set up some macros. Now, in the decoder, I said address space bits and so on. So what we're going to do is I'm going to say pound define RAM adder bits. 16 kilobytes is 14 bits of memory. Size 1U left shifted by RAM adder bits. Put this in parentheses. I like to parenthesize my macros because you never know what the context is going to be around you when you use them. And the mask is equal to RAM adder size minus 1. So address bits, size, and mask. There may be other RAM modules we could mix and match, and in which case having this here is a bad thing. So this is going from RAM to RAM 8, 8107X 8X4. There. So this is where you start getting motivations for higher level languages having namespaces. I would love to take this entire chunk of stuff and put it all in a namespace somewhere so that internally I didn't have to keep saying RAM 8107, RAM 8107, RAM 8107. The other way I could do this would be to lift these macros out into the source file for it, so that people declaring RAM wouldn't know the memory size, but that would mean one more round trip to memory on the host system, going from the pointer to this RAM structure to actually finding the memory. I want this in line, so it's going to be there. So either I have macros, which have a namespace on the macro name itself, or I hardwire the number. I'm not going to hardwire the number. So it is what it is. And like any good pieces of static RAM, when we power up, our contents are indeterminate. If you reset a computer with static memory, okay, it retains its stuff. Now this is actually a dynamic RAM, so I need to document this module does not yet model the effects of failure to refresh each row of the memory within checking. There's a period. If you basically you have to any given row of the dynamic RAMs, you need to read the row, do a read somewhere in that row, so that the chip itself will refresh, because dynamic memory cells have a charge and the charge leaks out fairly quickly. So I am going back to the PDF really quick. Time between refresh is 2 milliseconds. So if you don't read a row within every 2 milliseconds, if the row is sat there without any accesses for 2 milliseconds, the contents are indeterminate. But we're not going to model that. I'm going to assume that this RAM card has everything it needs internally to perform the memory refresh cycles. And row, basically of these 14 bits, there's 7 bits that are called the row address and 7 bits that are the column address. So to refresh it, you make any access with the row bits set. Okay, so there's 128 rows in this puppy. Well, 128 rows in the card. Now the chips, we are actually dividing this down. So the chip is it's 4,096 bits. That is let's see, insert format %X 4096. So that is 12 bits of address space, which means we have 64 rows. So what we would do to refresh memory is we would do a read. We would enable all of the chips on the card to do a refresh cycle, and we would present a row, and every 2 milliseconds we have to cycle through all 64 rows. We'll have to remember that for the future when we start to think about that. I'm thinking that I won't actually model dynamic memory refresh until I'm modeling a CPU that provides refresh cycles. I think it's either the 8085 or the Z80 that includes memory refresh cycles as part of its normal operation. It was kind of a cool thing at the time, and it went away because, well, I guess we no longer need it. At least I'm hoping that modern Intel CPUs and modern AMD CPUs no longer do anything special to emit dynamic memory refresh cycles. Anyway, so we're doing a static memory simulation because we're just saying, oh, the dynamic memory is inside the card. We're not doing it. All that to just say I'm not going to deal with this. Okay, so stock boilerplate. We verify the invariance as a valid pointer, valid name, and not an empty name. We're going to verify valid signals attached and no in a non-invalid configuration. So these are actually, we own these pins. I'm going to say that this board is going to present edges that it can connect up to someone else. We are not going to be, there's not going to be one read signal that's going to go to multiple boards because that's going to have those multiple boards gating all at the same time. We don't want to have multiple boards waking up and then using some other mechanism to work out which one does it. We're going to have all that logic in the decoder. So we get to own read and write. We don't own address and data. Okay, so initialize the given thing to have this name and initial state. Okay. That will initialize read and write to be in their initial state, which is going to be high. Then we're going to get called, we're going to get called and linked when we have the address and data set up, and that basically is just going to start doing our invariant checks. We do not have shadow. That's a decode thing. We do have a post. Make sure it's not completely broken. Do a more thing to make sure that the code is working, and we have a benchmark to say how long does it take for us actually to do a read cycle or a write cycle. And I am going to benchmark read and write separately. Trying to do a single benchmark that says the speed of the RAM is this many nanoseconds. It's going to be the same time in the simulated system, but in the real system, one of them does a read and the other one does a write. Subtly different effects in the cache and so on. The timing is probably going to be indistinguishable, but let's actually measure it and publish that. And there are all of our things. So now we go over here to .c file. I'm going to copy this whole thing. Oh, we do need edge and we do need support. We probably need more things. We'll see. These have been defined. Wherever we have extern, I'm going to do this. And we need to put in a thing called, we need to put in names. And I'm going to do the void RAM to do implement. Okay. Now, something that I have done in others is I'm going to put in the big comments from the beginning here. I keep going back and adding them in. I just realized I did a switch to the Sun font, and it's not effective, but my ligatures have gone away. Yeah, okay, whatever. So we now look more like my typical 1991 development environment than we did before. We need an address and a data that are going to be owned by the test. Static edge. we need a RD edge and a WR edge. And we are going to need a I shouldn't have made a name that was so hard to type. Test-init is going to set us all up and get us working, so we're going to up here need a static RAM. We'll probably need some more support. Power on self-test. All three of these guys need to do the power on self-test, or they need to do the init. They need to do an invar. Well, the first two do. Benchmark isn't going to run the invariance at that point. And for now, I need to say print top, print end, and what do we have here? RAM init is redefined because I put in the C file as well. It doesn't go there. Too few arguments to init. Well, that's because I'm not calling init here. I'm calling test init. This is why we test. So now the only things left are warnings. We have a bunch of things that are defined and not used. And I was going to put in the rest of these comments while I was scanning down through, doing the conversion from one module to another. Built-in self-test. Benchmarking, and way down at the bottom we have test support. And also here I have a static function which is just the same name but reversed. I'm going to end up with two of these because I'm going to do reads and writes. Okay, we're going to benchmark both of those. And for now, there's just going to be errors on them because they are defined and not used. And we are correctly running. We are idempotent on the build and the test. We have all these things that are defined and not used. So now we go back to the top and we start implementing this. What are the invariants for this? Well, I'm not going to start calling invar until we are linked. So we don't have any special invariants that we can check before we're linked up. We don't have a special state. So we just assert RAM. CSTR name equals RAM arrow name. Assert name. Assert name sub 0. So we have to have a pointer to a RAM. The RAM has to have a name, and the name can't be blank. Okay. We're going to assert RAM arrow adder. We can't assert anything about its contents because literally anything could be on the address bus. But we are going to assert that those are valid pointers. we're going to edge invar of ram arrow RD underbar. I just realized I'm only using name in a couple places, so it's pointless to do that. Okay, so read and write are both valid. I am not going to assert anything at all about the contents of RAM. I could do something silly like assert that its size is equal to RAM size, which would protect me against anybody changing this from an array to a pointer. Not going to do that because that's only important for performance, so it should be uncovered when we do our performance checks. And if somebody makes that change and they do it in such a way that our performance is still good, we shouldn't be failing any tests. So we're not saying we're required to have an array, we're saying we're required to be fast. So what else do we want to do? We want to assert, if both of these are low, we've got a problem. So we want to say assert EQ integer. One of them has to be high. So 1 is equal to ram arrow RD underscore arrow value or. So one of those two guys needs to be 1. So init assert ram name. So there's our entry and variance. Okay, edge init ram arrow RD underscore is going to be format %s colon / RD name. So that gives our read signal the appropriate name, and there's our write signal. Adder and data are probably still null because we are not linked up yet. I am not going to clear RAM at this point because I want it to be, well, wait a minute. What's the contents of a typical memory board when you flip the power on? In my experience, if it's truly a power on, it's all FF. This is most commonly. Of course, I used to use mainly static RAMs. Yeah, I'm going to set this to FF. If I set it to zeros, that would be an interesting way to start, but 0 is a rational initialization value that you might set it to. FF will tell me, oh, we didn't do this. So let's see here. For word a equals 0, a less than that size, plus a. Yes, this fails if the size is equal to 64 kilobytes. So, ooh. Let's use memset. And we are a CPU that is from 1975. And the size of it is RAM. Actually, let's use size of. So if RAM is a pointer, we're in trouble. So if RAM is a pointer, I need to malloc into it, and then I need to malloc the pointer. RAM is a bad thing to call stuff, so we're going to call this RAM data. Data is a bad name because we have a bus called data. Call it RAM cell. Cell, cells. It's an array. It should be plural. I'm liking this less and less. P byte cells equal to RAM cells. So don't I have a p byte? Oh, I don't have a p byte. P bit byte. Okay, so now we're back to having things that are defined and not used. This is useless. I think since I'm making that assertion instead of there. Let's put the assertion at the top. So if cells got changed to a pointer, this would now bonk on us. Greater than size of byte, p byte. So we're saying if it's a pointer, we're going to fail right here. If it's an array and the size has been mucked with, we're going to fail here. And down at the bottom, we're going to say whatever it is, we're going to clear it for its own size. Which means that, of course, if cells is a pointer and it's a null pointer, this will pass in the size of a null pointer and do memset at 0, we'll get a seg fault. We're happy. I could also say assert RAM cells not equal to null. Now the compiler should bitch about that if the compiler warnings are good enough, because even if RAM is null, RAM cells is not at the beginning of it. What included target? I didn't include target here. Does support.h include target? No, it includes headers. I included edge, which probably includes target. Yeah. But let's include target on our own. So I don't like transitive includes. I like that they work, but I don't like saying, I only compile if you include target for me. I mean, unless it's something like headers.h where the job of the header is to include a bunch of other things. I don't want to depend on getting other headers through edge. What I really love is I include all these things here. If I could say, when somebody else includes edge.h, they don't get this. I mean, these are only effective for the duration of edge.h. That would be really nice, but that would be a different language. So init, We initialize these guys. I am going to edge high each one of them. We're going to set the memory to FF, well, 255, and then we're going to say, boom, check the invariance, which would fail because we're not linked up yet. So we have to do that down here. So invar, we're going to start off with similar, but here we're going to sample the contents of the structure so that I can look at it properly. Okay, so invariance, assert name, name sub 0, adder, oh, linked. Oh, that's checked up above. So if I do the invar here, that will check and make sure all this stuff is good. I probably want to assert adder and assert data. Well, I'll leave the invar to do that. But what we want to do here is hook up our functions that will respond to reads and writes. And I'm going to model that right on here. So edge on fall of rd underscore calls ram rd fall. I'll just call this ram read, and I'm going to give it the whole name. Even though it's static, if I give it the whole name, then same things happen in the debugger. So I now have two static functions that I'm going to need for this guy. These get declared up at the top. And they get implemented down here. Okay. So this says error invalid initializer because I didn't need to be a p-edge. And unused variable cells, got it. And unused variable adder data, got it. And I use these only once, so there's no point. Got it. I never use name, got it. There. Okay, so bench defined but not used. To get rid of these warnings, I'm going to start retiring the warnings by pushing together this stuff. Decoder bench, for example, I do the test init. I want to do two of these lines. Actually, I'm going to do one line. It's going to say RAM 8107x8x4 double DT. And this is going to be the first benchmark, which is read. And I'm going to be dividing dt by something here. Okay, so now I need a work variable. Now these guys are going to initialize work to 0. And they're going to do something which will have to bump work as it does work. But at least this now means that we can get past things. Okay. So these are still defined but never used because our test init isn't actually doing the init. Oh, haha. Worse yet. The RAM owns its own read and writes, so we don't do that. However, inside test init, we do need to do that of RAM arrow adder equals adder, RAM arrow data equals data. RAM linked. Now test init gets called from benchmarking as well. Somebody else is going to run the invariants. See there? Okay, too few arguments to RAM init. Use the macro version, which will give it the default names and such. Run assignment to p adder. So data was defined as an adder. That's bad. That needs to be a p data. There we go. And we're running. We're not actually getting into the code yet because we didn't set up main yet. So wherever we have 8228, I'm going to add after where we have decoder, the line after it's going to be this RAM thing. RAM 8107 x8 x4. Okay, so the error in our build is now just we're printing post, we're printing bist, we're printing post, we're printing bench, so we can now take those out because we know we're getting into these routines. And there we go. And our times for these two functions are 1.1 nanoseconds and 1.0 nanoseconds. And that's basically the overhead of the benchmarking. We will be doing much more work inside the thing we are measuring to amortize out that 1.1 nanoseconds. We'll do maybe, I don't know, 100,000 accesses to memory, or we'll cycle through and read every cell in memory, and then we'll do that several times. But that will happen when we get this going. So we have connected this up. What does read do? Well, what read does, when we have a descending edge on the RD signal, I'm going to look in the address and set up data from that. So I'm going to say RAM arrow, star RAM arrow data is equal to RAM arrow cells of mask amper star RAM arrow adder. And this is the other way. This is the write cycle is just exactly the reverse. Now, these should take the same amount of time, frankly, because they're both computing the same two addresses, and they're reading from one and writing to the other, and the CPU doesn't care what order that's in. So, yeah. So once we get reads and writes going, we're good. So what I'm going to do is for post, I'm going to make sure I can read and write the first cell and the last cell. And for BIST, I'm going to make sure I can read and write every cell. Now, I could probably test every value into every cell. What I will do is something more like a barber pole test, where I'm going to write in, I'm going to write the entire RAM with a pattern that I can check that is not the same as the address. Thank you. And then I'm going to read it back and verify it's the same pattern. But post, we're just going to spot check. Now, I don't want to be writing the same bit of code over and over again that says read a cell or write a cell, read a cell, write a cell. What I'm going to do instead is check RD of RAM. I'm going to give it an address at 0. I'm going to check that I can actually check WRRD. So I'm going to write it and read it. So there's a single cell write read. And this will assign this value into adder, and it will do things and will verify that it's coming back correctly. So it will get masked. So we now have a support function for testing called static void check write read of, it's going to take a RAM and a adder, and a data. Oh, no, it's not. It's going to take a word, which is the adder, and a byte, which is the data. And now we go down to the bottom, and the test sequence is kind of simple. Oh, what do we need to wiggle for this? Oh, we're going to start by placing star adder. Now, instead of setting up things using RAM, whatever, I am going to use my globals that I set up. And so what I really do need is a static pedge rd underscore and wr. So the system surrounding it will know about a pedge. And now we need to set those up inside test init. There. So the way we do this is the system outside is going to say star adder equals adder, star data equals data. Oh, and I think I need to increment tau. Yeah, I need to increment tau saying, separate from anything else that has happened before, I'm going to set adder and data, and then I'm going to edge low of WR underscore. Okay. Now, since this is a test, I can actually go in and look at the RAM and assert that the right thing got put in the right place. But we're not going to do that. I'm not going to make this a white box test. What I am going to do is we are going to go to the next cycle, and I'm going to say edge high of WR. And when I'm doing that, I am going to invert data. So on the rising edge of write, the data is going to be corrupted. Okay? Actually, let's corrupt it with a 0125. So 01010101. We're going to muck with the data, and we're going to say edge high. I'm going to leave the same address in case it snaps something there, and then I'm going to say star adder. We're just going to leave the address stable through all of this. So data still has the corrupted value on it. We're going to do a low edge and a high edge. And here we are going to say assert EQ integer data star data. So on the descending edge of RD, we're going to get our data back. And then we're going to go high to release things. So there is our single byte write read check. And this says expected close paren before word. Do I have a data type called word? I have a data type called word, don't I? Oh, data type starts with a capital R. Yeah, the other thing about C is that even the most modern C compilers, it's not really gonna be nice about naming what's wrong. The error messages are never going to be good. Even Clang. Clang is a lot better than GCC in a lot of ways, but even so, raw C, it's just a small error can be, you know, if there's an error in the code and there's one clear correct thing it could be, which is determined from it, that's great. But often in C, an error in the code, there are several different ways of correcting it, and the compiler will do its best, and its best is often not good enough. So during the check, write, read, we actually are not referring to the RAM. We're just manipulating the signals we own. Note, we do, oh, so I could actually just eliminate that entirely. We may want to print out what's going on. So I will continue to have it. So if I wanted to print some more stuff here on test failures, I could. Come on. Put the keyboard in the right place. No, that's bogus. I really don't need to include RAM because this is the RAM test. There we go. Check, write, read. .8107 x8 x4 test WR RD. Okay, so post is now running, and it's checking that we can read the first byte and the last byte. And it would be nice to verify that those are actually different cells. So I'm going to break this up into two things. This is going to be a test write and a test read. Okay, so test write is going to say, set the address in the data, corrupt it, and assert that it's different. This is going to be assert that it's not equal to our data. Actually, the way we can do that is by saying star data is equal to data exclusive or 0125. And then we send the edge low, which would read, and then we're going to assert that it's equal. We're going to send it low again. So we're going to write 0, and then we're going to write, we do these in a different order. So we're going to write the first cell and the last cell, and then we're going to read them back, and they have different values. And then we're going to do the same thing with the other two values. Slightly redundant test. We're okay. So let's see, unused parameter adder. That's not right. There we go. Yeah, if you don't put adder on the address bus, bad things happen. So that's post. Now at BIST, I'm going to do something a little more exhaustive. So we're going to have two barber pole patterns that are separate. So if I keep using word for my addresses in my loops, that risks somebody grabbing RAM 8107 and creating 64 kilobyte RAM thing. So I'm going to just say for int a equals 0, a less than this value. Unsigned. Did I do any for loops? I used a mem set to. No, I didn't use a mem set. Yes, I did do a mem set. Good, 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 good. So my barber pole is going to be slightly weird. My data that I'm going to produce is going to be, I want to exclusive OR the upper byte with the lower byte, and then exclusive OR that with 0125 XOR A amper 0377 XOR A So there's barber pole number 1. Okay. And then we're going to do barber pole number 2, which is going to be a different pattern, where I'm going to invert A And I just realized those are going to cancel out. What I really want to do is invert the data that I'm writing. So instead of 0125 XOR it, I'm going to invert that. So this is 0252. So there we go. And that test is now passing. Let's make sure, print end. That's BIST, and we're going to verify post. And there we're printing it, so we know that we're getting to the end of those functions. Okay. So the work I'm going to do for reads is I am going to barber pole with every possible thing there. For unsigned, B is 0, B less than 0400, plus plus B. B XOR that, and read. We're going to do that for each B. And what I'm going to do here is the work involved is equal to the number of memory accesses that I did. So this is 0400 times 2 times RAM size. And that's taking a long time. I'm doing too much work. I think I need to just do this with a small selection of B values. How about I do it, instead of incrementing B, we'll start at 1. We'll say B left shift by 1. So 8 cases instead of 256. Much better. So this says that when I do that much work, the test read and test write are taking 0.2 of a nanosecond. That's good. But that's not testing read and write separately. So what I want to do is change this so that I'm benchmarking the read. I'm not testing the read, I'm benchmarking the read. So we're just going to benchmark read. Bench WRA equal to, and I will. So this would actually benchmark the time it takes me to do this computation, wouldn't it? Let's write a interesting value. Let's say a amper 0377. And the amount of work we're going to do. Oh, we need to set this up before we call the bench function. We don't want to do this within the bench. I will have a WR function and an RD function to do the benchmarking. When we're reading, we're not going to be comparing against anything, so I can read whatever is there. I can write whatever is there. Let's just benchmark writing zeros. So read and write need to be new functions, specifically for benchmarking. Being quiet here while I quietly tap out the things that need to happen. So, void conflicting types, unsigned int, unsigned char, and that conflicts with, oh, right, yeah, let's not conflict. Oh, better name. Okay. So when we're actually doing the work, this does boost up the RAM work to like 6.2 because I am wiggling a whole bunch of lines, and we know that takes some time. And iterating the bit through here is bogus. I just need to unsign b equals 0 reps. Get my hands misaligned on the keyboard, bad things happen. So that's the cost to do memory reads and memory writes specifically by manipulating the signals that we own. So read is increment tau, set address, draw edge low, grab the data, increment tau, and set reg high. Okay, so that whole sequence there, and this sequence is increment tau, set address and data, bring right low, increment tau, bring right high. Yeah, that's good. So is there something here that we haven't tested or benchmarked? We have benchmarked and tested these guys. This may be the entire RAM module. About an hour, including all of the testing and benchmarking that always takes the bulk of the time. So I am going to go ahead and commit this. I will add more comments off stream, but now I'm going to swing in and do the other thing that is similar to this, which is the ROM. So let's do Minix shell git status. So this says we modified main.c and target.h, and we added some files. So let's take a look at the diffs. Git diff-wu cat. This says main.c, we added our stuff, and target.h, we added the pointer types. That's good. So now we can say git add dot. Git. Oh, almost forgot. What change did we made to GNU Makefile? There. So basically, I had a problem where iNotify wait is still sometimes not returning when I modify a file, and I'm wondering if it's because sometimes when I modify a file and I save it from Emacs, it says, oh, you didn't actually change it, so I won't actually write to the file. But I am going to, yeah, let's undo that. I don't want to check that in, and rather than muck about, I'm just going to change that back and make sure that we did the right thing, make sure it still builds, we're good. Changing a new Makefile triggers a build, and we're still good. Git status. Okay, git diff dash cache cached. Oops, ccat is a crypto function. And by crypto, I mean encryption and not cryptocurrency, which has nothing to do with encryption. So checking over this really quickly, this looks like a good diff. We've got a bunch of files added. File added. We're good. Dash M. Git commit dash M add RAM 8107x8x4. Also add pbyte and pword, actually pbit, pbyte, pword types. Git push. Bada bing, bada boop. Sent up. Okay, next one is the ROM. Now, let me bring up my PDF again. We're going to find which ROM we want to pretend to be. And in fact, let's make this, this is running at 75%, so let's bring it up to size. And I want the pages to fit neatly. There. So, 8080 systems like ROMs. And they've defined some ROMs in here. So the big one is the 8316, which is a 16 kilobit ROM, mask programmed, 2048 words, so it's 2 kilobytes of memory. Access time is 850 nanoseconds, so this takes 2 T states to read, so this will need a wait state. So buckle in, we're going to be implementing wait states, which means we will actually be manipulating, believe it or not, the decoder, because I am going to have the decoder watch the signals for doing wait states, and everybody else can call into the decoder to do it, so we don't have every single ROM chip in the system independently listening for wait states. And my ROM board is just going to be this much. It's going to be one chip, which is going to be 2K by 8 bits, and we are going to need a way to program it. Now, the way you did this with Intel would be that you would say, I'm going to be buying 10,000 8316s, and there's actually forms in here for telling Intel what you want in the ROM. So that's the way we will specify this. We're going to pretend to be an 8316. We are going to, as part of initialization of the 8316, you will tell it a file name to read. And I think I am going to have that data in hex format, which is a neat little trick. I will have to look up precisely how to decode those, but the tools that I can find for assembling 8080 code will turn out the listing file, and they will turn out a hex file. So we're going to parse the hex file. So it takes 11 bits of address, and it does some wiki-wonky in here, and it says we're going to grab the data from the matrix, and we're going to decode which one we want, and then we're going to hold the output until the chip selects all match. And here's the really, really bare, simple timing diagram on the left. If the address changes, we have a delay of up to T sub A before output is valid. If the chip selects become valid, we have a change of up to TCO before my outputs become valid. If the chip selects change again to not match us, then we have TDF until they're not valid. So there's only 3 timing windows of interest here. So address change, so typically 400 nanoseconds, but up to 850 nanoseconds later, we've got our data. We can gate the data out. Chip selects, we've got up to 300 nanoseconds it might take for us to enable our outputs. And deselect, well, minimum is 0, so we're not going to float our stuff before these change. Okay, it's got to be after, and it may be up to 300 nanoseconds. So what I will do is when we have the read signal go active, I'm going to say, I need a wait state. But I am going to put in my data at the end of that wait state. So this is basically going to say, call me back in a T state. I think before I get started on this, I'm going to go refill something to drink because I am kind of thirsty, and I could probably use some coffee as well. So I will go get coffee and soda. And when we come back, I will start work on building a ROM of the appropriate size. I am fiddling around with the way things are laid out on my screen. We're going to leave the PDF up here while I go get something to drink, and I will be back. Oh, come on. I want to move the PDF out of the way. Thank you. I keep moving the editor on my screen to where the editor is no longer completely visible, and it takes a bit of nudging to get it in place. So I'll be back in a moment. Okay, I'm back. So are we ready to start working on this ROM? I think we're ready to start working on the ROM. PDF goes away. ROM looks a whole lot like RAM, doesn't it? So this is called ROM 8316.h. E107 x8 x4 becomes 8316. RAM becomes ROM. Let's make sure I don't replace the word RAM in the middle of a word somewhere. Yeah, program has RAM in it. I don't want to have program. I got an extra new line in there. There we go. So ROM differs from RAM pretty simple way. So this is a, first of all, this is a 2 kilobyte read only memory. Attach RD signals. So it's 2 kilobytes of read only memory containing a known preset content to the simulated system. Notionally modeled after an 8316 chip with some external logic providing that allows us to efficiently connect to the simulation. That's because the 8316 does not have just one simple bit that says do the read. So address bits, this is 2 kilobytes, so it is 11 bits. Name, address, data, read. We do not have a write signal. If somebody does a write to our address space, we are not even going to notice. Now in the real system, the chip would get selected and it would start working on things, but the chip selects would include the read enable. So we would not have the ROM writing to the data bus when the CPU is writing to the data bus. So we would still get all the logic flowing through the ROM to grab the data and get it right up to its buffers, but it wouldn't send it out. Okay, so ROM in var, ROM init, yada yada, linked, all of this is now done. So ROM 8316.c, include the RAM stuff. Change 8107 x8 x4 to 8316. Change RAM to ROM. There. And I'm going to copy the comments, which I have updated. The comment that I've updated. Invalid signals attached. Well, actually, we don't actually have signals that were attached. So valid signals exporting, being exported. there is no invalid configuration. We have a signal that's either high or low. So adder, data, read, no write, no assert. So there is our ROM invariant. ROM init is much like the RAM init. Everything is the same, but we no longer have a write signal. And to do fill read data parse a.hex file, set up cells from a.hex file. And I think what I'm going to do is I'm going to use the name of the ROM here to find the file. And we'll do that during initialization. So leave that as a to-do. Look in rom/name.hex. To do what is base address of ROM. So it's possible that I will have a program that will live in many ROMs. So each ROM is 2 kilobytes. What if I've got a program that's 19 kilobytes long? So what I'll have to do is when I initialize, I will have to have an entry for the ROM here that's the name. These will probably all be symlinked to each other with an offset. And I think that's probably a bad idea. So what I'm going to do instead is I'm going to say cstr file, hex file, and word my base, ROM base. So our init will have to take a base address of the ROM and the name of a hex file to read, and whatever data in the hex file lives at ROM base, we will do. Which means that here, I'm in my internal state, I'm going to need to have a word, which is ROM base, and I'm going to store cstr hex file. Okay, that way, we at least know what file we loaded. Potentially, we might reload the file into the cells. Potentially, we would use that for printing, but we're going to hold on to the name of the file, whatever we do. But that's kind of private stuff. And ROM base, we're going to use when we get the read. Well, when we get the read, we're going to ignore it, because if we get our read, we know that the high bits of adder should be us no matter what. And if we get shadowed in, we're just going to look at the low bits and do the access. So ROM base and hex file are merely for debugging and printing. So ROM arrow ROM base, and ROM arrow hex file equals hex file. To do parse hex file write cells to do for all data in hex file in at ROM base there we go. That's enough. That will tell me what to do. Linked. We're going to say, well, when we have a falling edge of RD, we're going to do the right thing. Now, how are we going to communicate with the other end of the world for a wait state? I think what I'm going to do is from this end, if I want a wait state, I'm going to, first of all, set the request. Okay, so we'll need to have edge RDY in. So we have an input edge. So we'll force ready in low, and then I'm going to reset my read signal. And actually reset the read signal and first ready in. And somehow the decoder is going to have to get control back on the next Phi 2 clock. Well, it's going to have to get control back at some point after it notices what's going on and reassert the read. Maybe the way to do that is for the control system to backdrive dB in, and for the CPU inside T wait. There we go. When the CPU does a wait cycle, it will reassert dB in if appropriate, which means that the control signal, the control guy, can deassert dB in so that it will get reasserted and get a new edge. Or during a wait cycle, we can force dB in low and give it another high. So we never get, there we go. We'll never get a descending edge on dB in. We'll just force its state to 0 and send out another ascending edge, which will force this back. So we need to force read low and set ready in, and everything else will just scan through. So we're going to be doing a little scummy thing with edge where we're going to change its value without actually having anybody have a edge. Watch out for that. Okay, so we may see values change without a edge. That generally will be where we're going to see an edge coming immediately. Which also means we're going to be doing things in decoder. So this means we're going to get a read edge, and we're going to get another read edge later on. So what I want to do is have a notion of what word is currently active. So word, adder old. So if we get a read edge and adder matches adder old, then we're good to go. If they're different, then we need to have a wait cycle to catch up. Which means that inside init, we want to set adder old to something. Now, adder old probably should be bigger than word so that there's a notion of adder old that's invalid, but we'll just start it out at FFFF. So what do you want to do here? Read. First of all, if ROM arrow adder old is not equal to, no, let's sample it first. So word adder is equal to ROM and before we do that, we're going to say p adder in uppercase is ROM. I like having things have the same number of characters. Old habit, it made things line up in my source code neatly, so it was easier to read. So if adder not equal to prev is equal to prev, this is the TW wait state. The read strobe that arrives during the wait state. Now, if this is the one that arrives, then we can say that, and we're done. Address, okay. So if the address is wrong, that we want to do is ROM edge low of ROM arrow RDYN. Pull DYN low to get a wait state. So when we get this in, we're going to set ready and high. We are done. We may end up getting an extra wait state. I don't know. We'll have to see how this plays. This is what I want to do. And let's reverse the order of these. So if the address isn't the one that we've been working on, then we're not ready. Otherwise, we're done. This also means we could put in a count. So we could say, I need 5 wait states for this ROM. Okay, so there's the read. We do not do anything for a write. Now, it's possible that this is all pipelined badly and that we'll end up getting 2 wait states instead of 1, and we'll work that out. Test support. We've got a ROM, address, data, read. We don't have a write, but we do have an RDYN. Now, RDYN is sampled into ready, if I remember correctly, shortly after phi2 rising. So dbn goes high, and we have a little bit of time. So that was the decision we made when we started mucking with our timings, was that we had some time between dbn changing and when the CPU sampled ready in. And that means that on the T-wait cycle, in that same location where it's going to bip and give us another rising edge on dbn, that we have another chance to look at ready and sample to ready. And this means I really, really want to have some way of displaying what's going on with these signals when we start hooking up the 8080 and actually having all of these things happen relative to phi. Test init, test read, test write. We do not have a write. We have data that we're going to prefabricate into our cells, and we will do test read and test read for bench. Things are getting, they're going to be complicated with this wait stuff. I'm not going to lie. So there is the proper declaration of ROM init. In order to set the initial contents of the ROM, we need to know our base address and the hex, the name of a file containing data that includes data in our range. So the hex file may contain all sorts of data, some of which is going to be within our range and some of which is going to be out of our range, and we need to actually honor that by storing only our bits. And we don't have something called add or old, we have something called prev. And test write doesn't exist. So post to do spot check ROM. So I'm going to fill the ROM with a barber pole. for the entire ROM, it's going to be the same expression I was using before for my primary barber pole. It's called a barber pole because if you printed out the contents, everything would be kind of marching one way. Then we say ROM test read. I'm just going to sample the first and last byte. These are probably going to fail because I don't know what the data is yet, but this is clearly not going to be 0 and 377. And this is not a test write. This is literally ROM arrow cells of A equal to this. Okay. Built-in self-test. Again, we are going to preset it with the barber pole. And we are going to then test read with that barber pole. We're going to do it again with the 0125, change to 0252, like that. So read for bench, we're going to do the same reads we were doing before. We are going to initialize it to zeros for the benchmark because it just doesn't matter. Actually, we're not going to even do that. There we go. Don't care what the pattern of data is. Just going to do this. Okay, test init. We don't have a write. WR underscore becomes RDYIN. Test read becomes that. We're going to do a lot more for test read. So we are going to assert that. We're going to toss garbage in there. And when read is done, we're going to say while RDYIN arrow value is equal to 0, because that's going to be set immediately when we come back. We're going to go tau plus equals 1. We are going to say RD underscore arrow of value is equal to 1 and send us low again. So Control N is what I'm trying to hit, and sometimes I hit a key that brings up Emacs news, which is I think Alt N or something. So if Radian is high or is low, then we're going to wait 1 tau. We're going to force RD to 1 and give us another low edge. And when it comes back out, we are going to say assert equal integer of the data that we see back because Radian wasn't set. We're going to step forward by 1 and give a rising edge on RD because that's the way the system's going to work. It is tempting that our decoder might never send rising edges. If we do that, then we preclude a future design where we actually track when data buses are driven by whom, when they're tri-stated, if there's multiple people. Let's keep the rising edges for now. And read for bench is the same logic with no assert. We return the data. We don't preload the data bus. Read, bump tau, do another read. Keep doing that until Radian is high. Read data and return. the default init. Base address is going to be, what do I want my base address, my ROMs to be if they're default initted? These are 2 kilobyte ROMs. How about I set them up nice and high, so the highest address in the system is 0177777. So I'm going to replace the bottom. So we're going to be 4 kilobytes from the top of memory by the default. Or I could say, there, okay. So we're going to take the top, what is that, a quarter of memory? 4 bits, top 16th of memory. Okay, top 16th of memory. Boom, there we go. And the hex file is going to be hex / #gen .hex. There we go. So default initialize is going to have a name, it's going to have an address, but really you shouldn't be doing that. So instead what I will do is gen and adder and core and base name. We will take gen, we will take adder, and base name.hex, like that. So the macro, ROM, tested it. We're going to start our ROM at the address, what? Let's put a ROM that loads from 0, and the base name is going to be fig4th. Okay. Because I happen to have fig4th handy. Let's pull that in. Live coding. First of all, we're going to make a directory called hex, and we're going to make a directory called fig4th. Okay. We're going to ignore everything in this directory that isn't explicitly checked in. Now, I have a copy of this in eSIM. This is the prototyping thing that I did. Doc. And these 3 files get copied into live coding fig4th. So we're going to have the potential to have a ROM that has the first 2 kilobytes of fig4th 8080. Now fig4th is actually fairly large. It goes up to this address here, 1B75. Which I believe is 4K. It's 8K, so we would need 8K of ROM to contain fig4th. And fig4th needs to be in RAM when it is running. So to do fig4th, we would need 2 of these ROM objects, one at 0 and one at 2K, and so on. And these would live in memory at some higher value, and we would then copy data from these ROMs down into RAM. That's if we want to do fig4th in ROM. We may not, but I'll do that for testing, because for testing, I'm going to need to work out how to read these hex files. And that's going to be simple enough to do because I have the source code for the 8080 assembler, which writes the hex files, and it's got some good documentation on what's going on there. But let's set these to 400. And then we'll do git add -- force. So we have those guys So this is the listing of the assembly of the thing. This is all just literal. My hat's off to the Fig4th people who in 1979 published this thing. John Cassidy and Kim Harris and all of these guys, just absolute heroes. And the fact that somebody managed to get a good copy of it set up on the web, it's really cool. All these resources. Now, this image actually presumes that it's running inside a CP/M system. So it starts at 100 hex, so 256 bytes in. The first 256 bytes of memory from 0 to 100 hex, CP/M puts some very specific things in there. And one of them is used by Fig4th, which is a jump to the actual BIOS. And there's a disk interface into it. There's a bunch of service requests that you can do to things like read from console, write to console, read from paper tape, write to paper tape, and so on. Set drive, so this is all CP/M stuff. Console and printer interface. We will be hooking these up to pseudo devices. There is enough information in this LST file that we can reverse engineer CP/M. Well, reverse engineer enough of its BIOS to do what we want to do. The other thing we can do is I have here the CP/M interface guide. Now, I had a copy of this. Okay, Gary gave me a copy because, well, my dad ran a lab at the Naval Postgraduate School. Gary was staff there, faculty, whatever. Anyway, and I wanted to eventually go to work for digital research, and that didn't pan out. I ended up doing other things with my life. But he actually gave me a copy of this way back when, and I wish I still had it. I really wish I still had it. It wasn't signed or anything. It was just, the document Gary gave me. But we have a scan. We have a kind of a scan. It's kind of low resolution. They like to do everything in this PLM programming language. So you have to read between the lines on a lot of this. And you have to infer a lot of what's going on. But between this document, which tells me all the function numbers and what they're supposed to do, and the Fig4th code that calls it, I can come up with, okay, here's the calling conventions, and here's where the pointers were. And I can use the actual correct name for things, which may or may not be in the Forth stuff. The Forth stuff's only going to have the things it uses. And this is for CP/M 1.4, which is the 1979 version that I like. Now, in amongst all of this somewhere, I think I actually have a copy of CP/M 3 image somewhere. It's not in this particular archive. Forth wants, I started dinking through, it expects at 0 there's a jump to the CP/M BIOS plus 3. And then we have offsets from BIOS plus 3. If I go look back at the PDF file again, I deleted the buffer, didn't I? Yes, I did. Anyway, the point is that Fig4th expects there to be this stuff at 0 from CP/M, and the only thing it really uses, I think it might use the file control blocks, but the important thing is that at 0 there's a jump to BIOS plus 3, and console status is at an offset of 3 from it. Console input and output read. So I'm thinking that this may be for a different version of CP/M. Set disk is at 018 hex. That is 16 and 8 is 24. So 24 would be function 12, lift disk head. Reset disk system. Select disk is 14. So 14, select, open, close. We've got open file, close file. So these are not the same functions as these. So yeah, these are offsets into the BIOS. So this is functions into the other stuff. Somewhere I have, in all of this, we have information about the BIOS itself. And yeah, maybe my information isn't as complete or consistent as I had hoped. So inside their examples, to print a character, we push stuff on the stack. We put something in C, we put the character in E, and we call BDOS. Okay, BDOS is at 0005. So at 0 is a jump to BIOS plus 3, and at 5 is a jump to the basic disk operating system, which takes a code for what you want to do. So there's a difference between using the BDOS and using the BIOS. And we'll have to worry about what's going on here in fourth, and we'll have to work out what's going on in the BIOS. So boot, warm starts. Surely there is information about that in here somewhere. I thought I saw it. Principal entry for FDOS is at location 5. That comes up to here. It's the BIOS that I'm worried about more, and it looks like I don't actually have BIOS information in this document. But that's all public information. You can come up with source code for CPM and binaries. A lot of that data has been recovered. But that's neither here nor there for anything that we are actually doing today. The interesting thing was just that I wanted a hex file. So we are going to move this hex file into hex. And let's set up our screen again. So in hex, we've got that. In fig4th, I've got that. I could actually carry these in the hex directory. No, let's keep them in fig4th. I may put a lot more notes in there. Fig4th should be a subdirectory of the doc tree. And again, in doc, we are only going to add things to doc that are explicitly added in Git. Okay. So Git status over here says new files. In this directory, we've got a bunch of things. Let's go back up to the top level to do this. So we're adding doc ignore, fig4th ignore, the assembly input file, and the list from the assembler output file. We've got a hex directory where we put our hex file, and we've modified the RAM files, and we've got new ROM files. So back to looking at the ROM again. So the point of all this is that we are going to test it by initializing it from the fig4th hex file, and then we are going to use it. And I am thinking that we may muck with it during the test. So ROM test WR does not exist. We do not write to the ROM. that does not exist. We do not respond to a write signal. So this is all compiling and running, sort of. I do not believe we are actually calling any code. So wherever we have RAM 8107, we're going to duplicate the line, and we're going to change this to ROM 8316. Boom. And we now have a seg fault because we haven't really hooked up anything. But just for fun, let's take a look at this. GDB of bin live coding. So again, GDB has selected the worst possible thing. So we're in subs here. Somebody's saying edge.c is saying edge low, edge to 0. And we're going to go up, and we're going to go up until we get into something that is recently written code. So the ROM says edge low of RD underscore. That's saying that RD is a null pointer somewhere. Because we forgot to set RD in test init. Well, no, we did it right there. Did I misread this? Edge to E, print E arrow fall, step run, print S. S is this. I is optimized out. S list. So we've got a null edge pointer that is on the list here. Print S. Start S says capacity is 8, length is 1, list sub 0 is print S arrow list sub 0 is that. Okay, we're going to recompile this without the optimizer. Okay, so now we go back to our thing, GDB. So edge 2 is looking at E, and E is null. So here E is null, edge low of null, edge low of ROM ready in. So ROM ready in isn't being set. Well, that kind of tells us what we forgot to do. ROM test init is setting ready in from ROM ready in. Well, that's not right. The surrounding system owns ready in. ROM imports it. So here we're declaring it, and this needs to be an edge because the surrounding environment owns the ready in for the ROM. And we need to initialize it. So edge init rdyn. Edge. And we're going to start out with ready in high. Now there are some invariants in this system we've already set up for ready in. So we're going to say grep-n ready in. So other people that use ready in, here, here. So edge in var of ready in 8224. And 8224 is expecting ready in to be 0 on power up. So rom.c low. Also means that if we want to be consistent, where we do linked, I'm going to have to also say assert 0 equals rom ready in value. So ready in is initialized to 0 by the system. It comes to 1. Part of the system startup for an 8080 is you bring the reset in. There's a reset line which is on a capacitor. It will go from 0 to 1, and it will trigger Schmidt trigger to come out of reset. But ready should be held at 0 until well after that. So your first fetch that you do will sit there and it will be in wait states. And then you bring ready high and you're off to the races. So we are going to assert that ready in is initially 0 when we get started here. Okay, so now this is running forever. Quit out of GDB. Let's rerun GDB, run the program. And I'm going to wait for it to just sit here doing nothing. I'm going to hit Control C. And we are here in step run. And this says that we are in the power on self-test at line 121, so frame 5. We're doing this test read. And nobody's ever making any progress from that first test read, probably because down at the bottom, in this guy, we say if ready in is 0, we're done. So somebody needs to set ready in high. Now, I am going to do that elsewhere. I think. No, I need to do, the ROM needs to set, ROM set ready and low, it needs to set it high again. Let's take a look at our logic here. ROM read says if address is not equal to previous, then edge low. I'm going to say stub, ROM, pulling ready in low. And set ready in low, set ready in high. Okay, that still runs forever. We're just going to do the loop check there, GDB. So in our output here, we have over and over and over again set ready and low. Because we never stored prev, we never stored our address into prev. Kind of an obvious bug. Almost like I planned it that way, right? That's my story and I'm sticking to it. Okay, so we didn't run forever, so we can let our terminal go do the loops. We can go back here to logs bench format and we can say we set the ready and low, we set the ready and high, and then we failed this test condition here. So we expected 0, and we got back 170. And 170 is our 252 pattern. So who's expecting 0? That would be power on self-test. So we wrote, look at this. Remember, I set this up and I said I'm going to sample it, and I never corrected my outputs. So this is a 0 to, let's say 170, you just said 252, right? And the other one is 82. Which is our 122, which is going to be 125 exclusive or the maximum address of the ROM, low bits, exclusive or the high bits, which comes out to 122. And now we get a whole bunch of those, and I can go down here and comment out these guys. There we go. So now that I have the correct test conditions in here, I probably ought to compute these. So first and last address is what we're checking. That's correct. Should have done that to begin with. These guys are now passing. These guys are now passing. We're now running the benchmarks. We are printing out 45.4 for our benchmark, which is that work. And so it's taking us 45 nanoseconds of host time to run the entire thing, which is this read for bench here. This whole thing is 8 times this. And what we are doing inside the loop are these guys. So go at tau, set address, bop the read. And if ready in is low, then we increment. We force read high so we can do another dropping edge on read. And data that out. Now this changes what I want to do with the decoder. Okay, so in the decoder, I also want to be watching phi2 rising, don't I? So I've got dB in. No, what I want to do is manipulate dBn during t-wait. So dBn will send me another rising edge. And dBn is going to be 8228.c. So what will happen is edge high dBn, blah, blah, blah. These are all tests. So on rise. So what will happen is that the 8080 will send us another rising edge on dBn despite the fact that it's already high. So we're going to force it to 0 and send a rising edge. So we'll actually just be sending out another series of calls on its rising edge thing to notify all of the rising edge waiters that, yeah, we're in a wait state and we're still high. You want to do something, you do it now. Okay. I am not sure if wait states apply to the write. The diagrams I've seen don't show a write with a wait state. So I think it's only reads. I think for writes you're expected to trap the write, but what if you're not ready to go? What if your write arrives and you can't handle receiving the data yet? So we'll have to look into that. So maybe writes will also do things. But that's going to be on the 8080 to send out another notification on dBn. And if write pulses low and stays low because we're in a wait state, we're going to do another descending edge. And if we get a start reads when dBn is already high before we started reads, well, we don't know what the state was before the edge anyway, so it doesn't matter. Is that we will edge low activated, and what I'm going to do here is activated value is equal to 1. So we're going to force another descending edge on edge low. And does this cause any tests to fail in the 8228? It doesn't. So we don't have any tests that say, leave my control signal low and run through one of these things and make sure I got an edge and make sure I didn't get an edge because it was already low, yada, yada, yada. But this will do what we want. Now start right, I'm going to do the same thing here. We are going to force a falling edge even if we were already low before we started. That will slow us down just slightly. And I don't think that's enough to worry about. But that means that we will be getting additional strobes here. So we are responsible for ready, and we pulled it low. We have to set it high, and we forgot to do that. Did we? No, we did. Okay, so if the address changed, then we need a T-state to deal with it. If we built a really slow ROM that required 2 T-states, what we want to do is make sure that we counted how many cycles we had that address, and when we got to the right number of wait states, we're done. Built-in self-test. Total ROM read time is going to cost us 50 nanoseconds of host time. That's entirely reasonable. I would love to make that faster. I don't think I can. I think we just have too many things happening for it all to happen faster than that. We fetch the ROM address, fetch the address, fetch prev, compare, store prev, edge low, else, mask the address, index into the cells, grab the data, write the data, done. So where is prev used? Prev is used in one place. Let the optimizer do the right thing. Where's adder used? Adder is used in multiple places. I am not going to trust that, well, it's not declared volatile, so it should just work. And this should just work. ADDR becomes ROM arrow ADDR. So back in the day, the thing I just did would have slowed us down because the optimizers were not quite as clever. But this should still be at 49.8-ish, 50-ish. 41, got faster. Now that's interesting. 43. So the trick that makes us faster with old compilers makes us slower with new compilers. Gosh, interesting. Now, If adder were declared to be a volatile pointer, then the compiler would have to assume that between this read and this read, the value might change. And I'm going to reverse the order of this comparison. I like the comparison order to be the same as the assignment order in these things where I'm saying, if this is different, do something. Okay. 44, 50, 43. Okay, I guess it was just that the time was variable. Maybe it really isn't faster. So what's left? Well, we still haven't read the hex file. So let me go grab my other editor over here and go find my ASM 8080 code. That may be in a completely different place. That may be over on my Linux partition. I'm on the Windows partition right now because I'm bopping back and forth between doing this and playing computer games today. See here, check my other. Users, far side, projects, on the other partition. Yeah, I guess that's on my Linux partition, which I cannot mount and look at from Windows because Windows doesn't support all of the decent file systems like ext4 and btrfs. So instead, what I will do, instead of relying on the sources, I'm going to see if I can get some documentation on the hex forms, Intel hex format files. ASCII text file with lines of text that follow the Intel hex file format. And there is a Wikipedia article on it. Does this give me enough information? Start code? It may indeed. Start code is one character in ASCII colon. All characters preceding this symbol in a record should be ignored. In fact, very early versions of specification even asked for a minimum of 25 nulls before the first record. That's because the hex files often were on paper tape. Okay, so you'd start streaming the paper tape in and you get a whole bunch of nulls and then you get a colon. Then there's a byte count. Oops. Even on the same live, so use my software comments, yada, 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 comment. Lots of Wikipedia stuff. Byte count, 2 hex digits, 1 hex digit pair, indicating a number of bytes in the data field. Maximum byte count is 255. 8, 16, and 32 are commonly used byte counts. Not all software copes with counts larger than 16. Then the address, which is 4 hex digits. Okay. Physical address of the data is computed by adding this offset to the previously established base address, allowing memory to be, okay, a record type, 2 digits, defining the type. I'm going to code this directly from the Wikipedia stuff. So I'm going to make something called hex.h, hex.c. What's hex? Parse the content of a hex file. Okay, so what we're doing is we parse a line, we get a start code. Oh, wait a minute. Was there anything before they talked about this? Okay, so when it says the physical address of the data is computed by adding this offset to a previously established base address, the documentation here has not yet done that. So we get the byte count, address, record type 00 to 05, data, which is a series of bytes, followed by a checksum in 2 digits. And then there's a very specific, here's how we compute the checksum, and then it talks about line terminators separated by 1 or more ASCII line termination characters, so each record appears alone on a text line. So one way I can do that is if I see a carriage return or a line feed, I can go back to looking for a colon. Okay, so hex codes. Okay, record type 0 is data. Record type 1 is end of file. 2 is a extended segment address. 3 is a, okay, so I am going to write some code here that just parses the file, and we're going to see where we go. So this is going to, there's going to be callbacks to store data. So we're going to say void hex parse, and we're going to pass in a cstir file name. We're going to add some more to this API as we go. First thing is I need to be able to open the file name. So file star fp is equal to fopen of file name. Okay, so if not fp, actually I'm going to say if not fp, then fprintf enable we're going to return something. So if not file, if not fp, return -1. Parse the content of, parse a named file in Intel hex format. Return value of -1 indicates an error with error no set. Okay. Something other than -1. So we have FP. I'm going to start reading FP, and well, one, if do I want to use fopen, or do I want we're going to be reading bytes? Yeah, let's use standard IO. So fgetc is our friend. So I'm going to just copy paste right from Wikipedia on this one. Can I? Now that's kind of bogus. So start initial state looking for the start code. So start code 1 character and ASCII colon. CH is equal to fgetc of fp. If CH equals EOF, return 0. Okay, we're going to do the returns in the middle here because I don't have break 2. I don't want to use goto. Normal case. So actually, this is not the normal case. So EOF encounter, EOF without a EOF record. stub. Early UF on hex file. Now, there's no error no I can do, so we'll print errors to standard error if the file is malformed. And return so I have a little program that prints out standard error nodes that everybody understands. So are any of these appropriate? None of these are appropriate. How about we say this? If there is an error, it returns -1 with error note set if the file is not found, or set for some errors. If the file is malformed, prints a message to standard error and returns -2 for it's complicated. Okay, there we go. Notice I'm not using fgets because I'm processing one character at a time. So we have now seen the initial state. Next one is byte count, 2 hex digits, indicating the number of bytes in the field. So int byte count. CH is equal to fgetC of FP. All these are going to do the same thing. What we really want is a throw. I really want to call a function to get the character that does all of this logic. So static int so I am toying with the idea in my head of using a long jump. And I have successfully convinced myself to not do it. I think I am just going to... Experienced users will know what's wrong. So I could use fscanf. fscanf is full of landmines. It's very, very, very capable. And it is also capable of completely blowing you out of the water if you're not careful. And I do not believe I can remember enough about fscanf, having not used it in decades. So we are going to need here a getInt, get byte. Call it getHH. So I'm going to read in 2 hex digits. So we've got int c1 equals fgetc fp. If c1 is equal to EOF, return -2. Int c2 is equal to fgetc. Okay. C1 is equal to H2D of C1. If C1 is less than 0, return -3. So returns -3 if non-hex if expecting character should be a hex digit but is not. So getHH is going to return the byte, or it's going to return -2 or -3. I'll call this fgetB. So I got fgetC and fgetB. There we go. So that's got the byte count. Then we got an address in 4 digits. Notice the lack of throw. This is why throw was brought into C++, because this is really do something, check error conditions. Do something, check error conditions. It's a mantra in the C world. Now let's make absolutely sure that this is most significant followed by least significant. So 10 is the length, or the byte count. There's our address. That's correct. So there's the address. And this is going to be, there's a externally provided base somewhere, so we're going to want that. So int base equals 0. Notice I'm doing all this with signed 32-bit integers because I am crazy, crazy, crazy. Okay, so record type is in 2 digits. Okay. And now we have data represented by one pair of digits for each one. So for int I equals 0, I less than byte count, plus plus I, int data equals f get b fp, if data less than 0, return data, stub to do adder equals ox, actually O% O, and the number of digits I want for octal is 6 digits. Data is %04 O. There we go. So we're going to hook this up a little bit. To the ROM. I need H to D. I'm going to allow the hex files to be in lowercase, and otherwise we say return -3. Int hex parse and int hex parse. Oh. Okay, so that ran. So now we've got ROM. And I've got lunch coming, so I'm going to rush through the rest of this little bit of code. So inside the ROM init, you got this to do parse hex file. I am now going to go in and I'm going to say hex parse of hex file. To do callbacks to store data. Okay, so the problem is hex/figfourth.hex, no such file or directory. Well, that's because the name is wrong. That's because it's got dashes in it. So also here, in base name, I do want to have that. We'll do that. This is the string fig-fourth-8080. Okay, that needs to not have a new line. And now we're going to have all of these things. I am going to take a break because we're almost 3 hours in. When we come back, I'll finish up the hex parser, which is not complete yet. I mean, we've got our data. We haven't checked our checksum. We really shouldn't call back with data until we've parsed the entire line and we've got the checksum and we've verified the checksum, and then we can call back with, here is some data. And we will do that when we get back after I've had some lunch. And I will see you then. So until then,